So in the last class, we had started discussing tension member design, right? So what are the provisions for designing tension members? And there were three limit states primarily that we were talking about. The first limit state was the limit state of cross-section yielding. Right? That is the first one here. This one, cross-section yielding, and it is given in clause 6.2 in IS 800. That is equal to design capacity of the cross-section yielding. G corresponds to cross-section yielding. D corresponds to design capacity. That is equal to Fy of the material, A gross divided by gamma M0. Okay, gamma M0 is the limit state, is the load resistance factor, for limit state of yielding. Okay, the other limit state was the net section rupture, and the net section rupture plays a role when you have a non-uniformity in the cross section. Right? If you have a uniform cross section, then the net section rupture would not govern. So in case of a reduction in the cross section, then you need to account for the holes or the reduction in the cross section. So you have to calculate the net cross section, that is AN, net cross section area, multiplied by the ultimate limit state, that is FU, ultimate strength of the material, divided by the resistance factor that corresponds to the limit state of rupture, multiplied by 0.9. And in the previous class, we discussed where does this gamma M1 come from, or what is the rationale of keeping gamma M1 larger than gamma M0 that we discussed. Also, this factor 0.9. So I'm not going to repeat that today. We have had enough discussion. The video is uploaded. You can go there and check. Now, if there is only a single hole in a plate, or if there is a series of or row of holes, they are all aligned in a direction that is perpendicular to the loading direction. So if there were like only these three holes were there, these two holes were not there, then the calculation of AN will be pretty straightforward. But if these are staggered, then you have to use, you have to calculate the path of minimum resistance, and that may not be a straight path of minimum resistance, that is the likely rupture path, but it may be a zigzag path. And in that kind of a condition, you have to calculate the A net, which was calculated, which was the expression for which was given here. Okay, the same expression is also applicable, is used in the US as well. So AISC 360 is the American Institute of Steel Construction. That is 360 is the code number, like our IS 800. So this is the code that is typically used for buildings and towers, etc., for designing steel buildings and steel towers, primarily for buildings. Okay. So that they also use the same expression. Then we had done this example where we calculated the minimum, the load path of minimum resistance, or the possible fracture path in this plate. So the plate was subjected to tension. The possible paths could be ABC or ABD or AD. And between the three of them, we found that 2.46 inch square is coming for the load path ABC. So that is the path of least resistance or least strength. Then you can calculate the full capacity. So the two limit states that will govern is the cross section yielding and rupture of the net section. So for the cross section yielding, this is the expression Fy Ag by gamma M0, and net section rupture, it is 0.9 Fu An by gamma M1. Substituting the respective values, we find that in this particular case, the limit state of yielding is governing. Fine. Then there are two other types of limit states that we wanted to talk about. I had started some discussion on one of these types. This limit state is not really a separate limit state. It is actually a part of the rupture limit state. Okay, and this is described in clause number 6.3.3. So 3.1, clause 3.6.3.1 is for net section rupture, but that is applicable. This expression is applicable when the stresses are uniform. Okay, so there is no shear lag effect. But there may be some shear lag effects. Then you have other limit state, which is described in 6.3.3 in the code. If you have a hard copy of the code, please keep it open side by side and go through it. Okay, you can reach 6.3.3. Also, there is another limit state which is given in 6.4.1, that is block shear failure. So we will talk about block shear failure in a minute, but first we will discuss the shear lag effect. This is also kind of a net section rupture limit state, but it has a combination of rupture and yielding. That's why it is marked as a separate one. This is IS 800. You had 6.3.3 and you have 6.3.1. So 6.3.1 has your limit state of rupture. So 6.3 corresponds to all the limit states of rupture, right? So 6.3, within 6.3, you have rupture of a plate uniformly loaded. 6.3.2 is the rupture of the threaded rods. 6.3.3 is for single angles. Basically, what it means is that there is a shear lag effect. Okay. Then you don't have a you have 6.3 for 6.3.4 for other sections for which some equations of 6.3.3 can be used. There are limitations given here. And then 6.4 is the block shear. So basically you have 6.2, which is cross section yielding, 6.3, which is net section rupture, and 6.4, which is the block shear failure. So we are talking about 6.3, but within 6.3, we are talking about the possibility where there is a shear lag effect. So last time there were some doubts about how does a shear lag effect come into being. So maybe I'll explain through example this time. I'll try to be a little bit more detailed about it. So you have this angle here, right? So this angle you can see in the bottom.
Yes, sir.
Yeah.
Yes, sir.
So in this angle, if you imagine that this angle is pretty long, right? It is extending on both sides. But of course, since you have 4 bolts here, these are the location of 4 bolts. So this is one end of this angle, this line that I'm drawing right now. That is one end of this angle. Okay, the other end of the angle is pretty far from here. And then you are applying some tension force on this angle. Okay, and that tension force automatically should be around the centroid or near the acting near the centroid. Okay, that may not always be true, but we are assuming that to be true here. So now what is happening is that away from this joint, somehow the stresses are almost uniform, and if they are not uniform, the angle will bend in a way so that they become almost uniform. Okay, but right near where the joint is, this is where it is tied. This angle is tied to, let's say, some kind of a gusset plate. That gusset plate is behind the angle, so I'm drawing it in a broken line. Okay, that gusset plate, the plane of the gusset plate is parallel to this plane of the angle. Okay, and to this gusset plate, the angle has been connected through these 4 bolts. Now, if the total force was T, how much would be typically you can assume each bolt to resist, assuming that there is no flexibility in the member between here and here and here and here. How much force will be there in each member, in each bolt?
T by 4.
T divided by 4 from each bolt, right? So now if I can draw it, let me. So if I can imagine, so basically what is happening is that you are applying a T force here, and you are applying a T by force on this angle here, and here, and here, and here. At all these 4 locations, you are applying T by 4 each. Okay, so if I take a look at the cross section at any of these places, right? So this is my cross section 1, this is cross section 2, this is cross section 3, and this is cross section 4. So at first cross section, that is cross section 1, what would be the force in the member, in the angle? There will be some tension in the angle. How much tension will be there?
T by 4, sir.
T divided by 4. Very good. At cross section 2, this will change to T divided by 2. Now 2 bolts are, the force equivalent to 2 bolts is acting there, right? Now at 3, and similarly at 4, I mean, you understand this already. So at cross section 4, you would have total T force. Okay. So which cross section is the critical one between 1, 2, 3, 4?
Fourth one.
Fourth one, right? Of course, because yes. So if it has to rupture, it should rupture at 4th. It should not rupture at 1 or 2 or 3, because the cross section was same between 1, 2, 3, and 4, but the force at 4 is much higher. Agreed? Fine.
Yes, sir.
Yeah. So now, if we look at how the force, so away from 4, let's say we have moved far away from 4, and we are saying that stresses are all uniform. So we have moved away from the joint, and stresses everywhere are uniform. Okay. So if that is the case, that means initially the stresses were only here on this leg, on the bottom leg, on this leg, right? But later on they get transferred to the other leg, isn't it? So that means what is happening is that what might be happening is that this force that is applied, so for example, any force that is applied here on this angle, it gets distributed slowly to the entire width. Then this force also gets distributed to the entire width. This force also gets distributed to the entire width. And this force also gets distributed to the entire width. Okay. So what do we know from here? So when we are, and we know which cross section is critical. We know that this cross section is critical right here. So at this critical cross section, we know that the force T4 that was coming from the first bolt, that has almost gone and gotten distributed, and the other leg has been loaded with that force already. Hopefully, I mean, we don't know at what rate it is distributing. That is a matter of analysis and research, and people have researched that. But we can anticipate that if the joint is longer, that means you have a large number of bolts. Then by the time the last bolt comes, that's where your critical section is. By the time you reach your critical section, the forces that were arising in the first bolt would have been more or less uniformly distributed. Generally, the rule of thumb is that if you have a lateral dimension of D, then by 2D length, you distribute the loads uniformly, or the boundary effect goes away. That is just a rule of thumb. Okay, so by certain distance, the other leg must have been loaded with these stresses decently, right? So this would have worked. Even some of the stresses from the second bolt also would have been transferred to the second leg. But the forces that were transferred from the last bolt are still completely on this leg only. And only a very small portion of the third bolt would be there. So basically what it means is that if you had only one bolt, let's say I had only one bolt in my joint. So if I had only one bolt out my joint, then where would have been the critical section as far as net section rupturing is concerned? Right here, or passing through the joint, passing through the hole actually, rather than. So it would have been passing through the force would have been acting right at this edge, and then the net section was passing through this hole. So now the net section is here, and we know that at this point the entire force is still in this leg. The force has not been transferred to the other leg at all. So in that case, the shear lag effect basically, so what is happening is that when the force is not transferred to the other leg, the entire force is carried by a single leg. That is what is called shear lag effect. And it will take some distance away from here in this direction before all this force gets uniformly distributed to both legs. Right? So that is the deal. So if you have a single bolt, then you have a more severe shear lag effect. But if you have a large number of bolts, let's say 4 or 5, then you have a less severe shear lag effect. Okay? So either you can say you have a larger LC, that is length of the bolt, or you can say you have more number of bolts. They are basically, approximately, they mean the same thing. Right? You cannot put, if you have a joint with 2 bolts, you don't put 2 bolts far away from each other. You try to put them close to each other. That's how you call that a single joint. Okay? So either you say your LC is larger, or you say that you have large number of bolts in a series. Okay, both of them reduce the shear lag effect. Fine. What else may play a role in controlling shear lag effect?
So bolting
the
outstanding leg with that plate.
Bolting the outstanding leg. But if you're bolting the outstanding leg, then there is no issue at all. There is no shear lag. So if your gusset plate, only if the outstanding, this is the outstanding leg. And this is the connected leg, you can say. So the outstanding leg, only if it is not bolted, that's what the case we are talking about. If it is not connected to the gusset plate, only this leg is connected to the gusset plate. How close we are to this edge? So the connection, if it is very close to this edge, then the shear lag will be less, because it will get, the stresses will be getting transferred to the other leg quite easily. So we are introducing less eccentricity. But if we are far away from that edge, like here, then if the holes are here, then we are transferring very little force to the other leg. So that is also one parameter. Likewise, there are a few geometric parameters. Thickness also plays a role. Thickness versus the width. So if this width, we can call it B or W. Call it B. Excuse me. So how much is this B value? That also will play a role, because if B is larger, you will have more shear lag, right? So that is where, from where we get this shear lag effect expressions. And these expressions for shear lag are readily available only for angles that are loaded or that are connected with a single leg. For other members, say you may have an I section like shown here. So in this particular case, you have one I section which is loaded. It is loaded concentrically, but it is connected not uniformly. It is connected only through 2 flanges, and some portion of the web will not be loaded. So if you are looking at tension capacity in this particular case, the cross, if I look at the I section, the critical section in the I section is somewhere here, right? And at that time, the stresses are not uniform. Stresses are more like this at that section. So from net section rupture point of view, I have a reduced capacity because I have non-uniformity in the cross section. But the expressions directly available, that directly usable expressions are not available in the Indian IS 800 code. You may have to refer to some specialized literature, some research or something. But for angles, that is because that is a very, very common type of a configuration. And you also introduce a significant eccentricity, which was not there. So in case of an I section, you had non-uniformity of stresses, but the stress distribution was still not eccentric. It was concentric. It is symmetric, right? In this case, you are introducing an asymmetry, an eccentricity, because this leg is heavily loaded and this leg is lightly loaded. So you are introducing an eccentricity, and therefore it becomes a very critical condition, critical limit state, and there are ways to check for it. So the older provision of IS 800 had this equation. The design capacity of net section rupture of an angle that is connected through only one leg, the formula was design capacity is equal to alpha an fu gamma m1. So divided by gamma m1. So an is known to us, the net section cross section area. So you just take out the area of the hole, that is an. Fu is the ultimate stress divided by the limit state of divided by the resistance factor safety. Okay, the additional factor alpha accounts for or takes care of the shear lag effect. And what alpha was? Alpha was taken as 0.6 for 1 or 2 bolts, 0.7 for 3 bolts, and 0.8 for 4 or more bolts. So as you can see, as I was talking about it, if you have more bolts, the shear lag effect will be less. Or if you have a longer joint, the shear lag effect will be less. If you have a shorter joint or fewer bolts, then you have more shear lag effect. If there is a more shear lag effect, that means net capacity will be lower, and therefore you are penalized by using by having to use an alpha value of 0.6. Now in the revised code, this equation, so basically this equation was found to be inaccurate or rather unconservative, and it has been substituted with this revised equation here. By this equation here. Okay, I'm sure you can see this equation in your IS 800. So this was rather unconservative or not very accurate, so it has been substituted with this equation. And what the code says is that for proportioning of the cross sections, you can use this equation, but when you are actually designing, you make sure that you satisfy the requirements of this equation. And since this one is unconservative, sometimes you have to be careful, and you should be using this equation. Even though I'm not a big fan of this equation, this is a bit too complex an equation. But I mean, I hope it is. I've not seen the literature from where it is taken, but I hope it is accurate enough. By the way, in this particular equation, TDN, the design capacity of net section rupture for an angle that is connected only through one leg, there are two parts. The first part corresponds to rupture of the connected leg, and the second part talks about yielding of the outstanding leg. Okay, so A and C here corresponds to area of the net section of the connected leg. Here AGO corresponds to area of the gross section area of the outstanding leg. Okay, and correspondingly you can see that two different resistance factors of gamma M1 and gamma M0 are used, because this is yield limit state, so gamma M0. This is net section rupture limit state, so gamma M1, and 0.9 also, that always accompanies net section rupture. Okay, so it's pretty straightforward. The only issue now is that the additional factor beta, right, and the rationale of saying that the connected leg will rupture but the unconnected leg will yield, and that is my limit state. Okay, so can anybody attempt to justify this rationale that the connected leg in an angle, this is the connected leg and this is the outstanding leg? So what this expression suggests is that the member will be considered as failed when this section, this portion ruptures, and when this portion at the same time yields. Not completely, because we are also bringing in a factor beta, but it has got something to do with the yielding. Yeah, anybody wants to try?
I mean, the unconnected.
Is that Lohit?
Yes, sir.
Yeah, try.
Sir, maybe you're asking why the unconnected leg is subjected to yielding, and I mean we are considering yielding, and the connected leg is limited.
Yes.
So because for outstand leg, it takes some distance for to, I mean, to take, it takes some distance to gain over the entire stress. But for the connected lead, the stress remains from the initial part of the portion. Maybe in that way, maybe. So
Yeah.
a connected leg is more severely loaded than the outstand leg. Maybe that may be the reason. I don't know.
Yeah. I mean, that's what exactly I had told before, but it does not quite explain why they are considering yielding for the other leg, outstanding leg.
Yeah,
Uh,
because the unconnected leg is not. It's not. The holes are not there in the unconnected leg, no, sir. I mean, holes are there only in the connected
but
leg.
the next section has to rupture, right? So if the next section has to rupture, if, for example, if this was a uniformly loaded cross section, right? Somehow you are loading it uniformly, let's say, and there was a hole, like you had an angle which is uniformly loaded, but somewhere in the middle you have a hole in one leg, right? Then still you would consider the net section rupture of the entire cross section. Right? Okay, so the idea here is that, and that's where the strain hardening parts plays a role. So what happens is that the leg that is connected from where the load is being transferred through the leg through which the load is being transferred, that is of course going to rupture. So there is not much doubt about where this part of the equation is coming from. 0.9 ANC FU, because we are talking about net section rupture. So one leg has to rupture. The leg that is at higher load will rupture, and there is no major doubts about it. You can see the mouse, right? You can see the cursor.
Yes, sir.
Okay. Now the doubt is why is the other leg, the limit state of failure for the other leg is considered as yielding, and then if additional factor beta is brought in. So beta basically corresponds to the non-uniformity of stresses. So you can see that stresses will be not uniform within that leg. So beta corresponds to that, right? So even if the edge of this angle is yielding, right, the rest of the cross section may not be yielding. So it is something to do with that this edge starts to yield. At some point, it starts to yield. Okay. And so basically what it is saying is that, okay, one leg will definitely rupture. The other leg, when the first leg is rupturing, let's say this is the last board, so that's where the rupture will happen. That is the critical section. So with this leg, when it is rupturing, the other leg, even though it is at a lower stress, in order to maintain compatibility of deformation, this will be higher stress and this will be higher strain and this will be lower strain. But no matter how low it is, it cannot be so low. This strain cannot be so low that it is not even yielded, right? Or at least a part of it must have yielded. Why? Because for rupture, you require a strain of 20% or 15% or something like that, correct? So in this location, you are at 15% strain. How much strain do you require to reach yield point? 0.0012 if it's mild steel.
Yes, sir.
Right? Let's say like 0.002. So 0.002 versus 0.2. What is the ratio of this strain, yield strain versus rupture strain? Rupture strain is how many times the yield strain?
0.012.
Rupture strain is how many times the yield strain?
Just 100 times the east.
Yes.
100 times. 100 times.
So that is
100
20%. Good. So I'm taking a conservative value here. It is otherwise even higher. I'm taking 0.002, but for mild steel, it is actually 0.012. Oh, sorry, 0.0012. So you get almost 100 value. So what the code is saying basically is that when this section ruptures, the other leg would at least start to yield, because you cannot have a strain difference of 100 times between the two legs when both of them are loaded in the same way. Okay, even though it is at a lower stress, in order for it to deform so much, this one also would have deformed at least a little. And even if it is 1/100th of this strain, it would have still yielded. Okay, so that's why you are taking a yielding. But then you are taking a beta factor to account for this non-uniformity of the stresses within the section. And that beta factor, basically, if you look at it, as I had mentioned before, if your LC is long, this is the expression for beta. Okay, and then there are two limits given for it. By the way, these are the two limits. So this is the expression for beta, that is as it is reported here. then there is one limit that it should be more than 0.7. You cannot take beta to be less than 0.7. That means you cannot take less than 0.7 times its capacity in cross-section yielding, this less capacity. In addition to that, also there is an expression that it should not be, it should not be more than points. It should be more than that. It should not be less than, and it should not be more than 0.9 times this value. Okay. So here the expression is wrong. It needs to be corrected. There is also a corrigendum that has come out with IS 800. If you look at that, it corrects that expression. And instead of FU gamma M0 divided by FY gamma M1, it says 0.9 times this value. Okay, so make that correction in your code, please, because if you use in the exam, I would expect you to use the correct expression here. Fine. Okay, so now if you look at, so anyway, these I will not discuss too much. Of course, these are all basically empirical. This one is of use for us. So the beta here, LC has a role to play. So if your LC is larger, that is length of the connection is larger, okay, then this LC is large. That means this portion, this expression is small. For a larger LC, this one becomes smaller. That means this part, because here this portion is in negative, so this total beta value becomes larger again. So for a larger LC value, your beta is larger. That means if you have a longer connection, your strength of the connection is higher. Fine. That means shear lag effect is less. Fine. Similarly, BS. If you look at BS, the expression for BS is given here. It is hidden a little bit. So BS is basically how much of eccentricity you have in a way. So it is W, that is this length, plus WL, that is this length of the connected leg from the point of connection, minus T. So if it is a bolted connection, then this is the location of the bolt, which is, and probably you have a row of bolts. So other bolts are right behind it. Okay. And there will be this portion which is effectively outstanding, and that is your BS. So if your BS is larger, that means your beta is smaller. That means you have a less capacity. That's what I was talking about. Right? So these two are main important geometric factors. Plus you have W by T also. So if your W by T is larger, again you have a smaller beta, that is less capacity. Right? So if this is thinner edge, then it will not have a significant contribution. Coming to other type of a connection, so either you may have a bolted connection where you have a single row of bolts connecting it, or you may have welded connection. So if you have a welded connection with the gusset plate, so this bottom one is the gusset plate in both cases. So if you have a welded connection, it's very common to have welds on both sides. And since you have welds on both sides, this edge is already connected completely. Then the only outstanding part, that is your W, becomes this one. Right? So this becomes your W. And that WL in this case, this is your W, this was your W anyway, and BS becomes equal to W because your WL and T don't have any role to play here. So your BS is reduced this way. Okay, that is for a welded connection. Fine. Any questions?
Yeah, I have one, sir. Excuse me, sir.
Yeah.
Sir,
Yeah.
is there any reason for thickness being a part for this CL lag effect? That's why.
You mean W plus WL minus thickness, this T value?
No, sir. I mean, why is there any reason for W by T being a factor for determining beta?
Okay, if W by T is larger, that means your beta is smaller. That means your, yeah. So basically what happens is that if you have a thin leg here, okay, versus a thin and very long leg, okay, so that is like W is large, but T is small. Then what will happen is that the eccentricity of the stress will be more significant. Okay, but if your T is more and W is less, that means whatever stresses are getting transferred, it will be carried very easily with this by this leg. Okay, so there will be higher stress concentration in this area if your T is more, but if your W is more, then there will be a lot of length of this angle which is not carrying any stress. And as a result, your shear lag effect will be more. And that's why you have this W by T factor. Okay. I hope I answered your question. No? Vishal? Vishal, can you hear me?
Yeah. Yes, sir.
Okay.
Thank you, sir.
All right. So, any other questions?
Sir, I mean, this formula is for only linear. I mean, the straight bolts, no, sir. I mean, this formula is not applicable for staggered. Staggered.
No, no. So this is available only for a single row of bolts. If you have in angles, it is not very common to put too many bolts in a single leg because angles, I mean, general sizes are such. But sometimes you may have like staggered kind of a bolt set of arrangement of bolts in a single leg. No, but this formula is not developed for that case.
Do people use staggered bolts in angles? I mean, I'm generally asking.
I have seen it to be used very like in a tower, for example, in a truss and all. Like if you're talking about a roof truss, generally you don't need those many because generally your requirement is mostly satisfied with 3 bolts, so you don't need too many bolts. In towers, I have seen because see angles are anyway very small members, small cross section size members. You don't have very heavy duty kind of angles. If your requirement of forces are such that you need, let's say 10 bolts, then most probably angle will also not work. Okay, so then you may have to go for something much heavier, okay, like a box section or something. So I have seen in telecom towers and transmission towers right near the foundation, right, at a very low level, there people have used, I have seen people using more than one rows of bolts because those angles are almost something like 100 millimeter by 100 millimeter or so. So you are almost 4 inches. So you can put staggered bolts or 2 rows of bolts. But yeah, I mean, then basically you have to refer to some specialized literature. You can do finite element analysis and figure out how much shear leg effect you are getting, or make some kind of a conservative guess. So if you have 2 rows, you can assume that you have only 1 row. All the bolts are in a single row, and assume then to be farther from this edge, something like that. So with that assumption, you can be conservative and still use this formula. Right? Makes sense, right?
Yes, sir. Yes, sir. Thank you, sir.
Okay, fine. Can I move forward now?
Excuse me,
Sure,
sir.
sir.
Yeah.
Sir, why can't we use plates instead of angles as there is no shear leg effect in plates as compared to angles?
Yeah, but see, angles near the connections, angles are a problem, but angles have stiffness in both directions, x-axis and y-axis, right? Flexural stiffness I'm talking about. So because angles are often designed to be to work both in compression and tension, and there are various advantages of angles actually. Angles give you 2 perpendicular surfaces to bolt with. So especially, let's say, imagine a telecom tower. Now your main legs, if you use a plate as a main leg, first of all, compression when you apply compressive force, the plate will have very little resistance in the weaker axis. Angle would have a much higher resistance. That is obvious. Secondly, you have got 2 perpendicular surfaces if the main leg of a tower is an angle, you have got 2 perpendicular surfaces to which you can connect your horizontal members, braces, everything. But if you use a plate, then you don't have those surfaces to connect with. Right? So therefore, angle geometry is a very, very, very connection-friendly geometry. The only challenge with angle is that it introduces that eccentricity for which you need to account for. See, the purpose or the objective of a designing exercise is just not to make the efficient design that cannot be really built on site. So you want to also have a design which can be built on site. And almost 60-70% of the times, your choice of the connection or choice of the member, it does not depend on which design is the most efficient one. It depends on what can be built, what is available, and what can be built on site. Right?
Sure, sir.
Okay. So just to draw your attention, so we have got this expression in the Indian code for tension, for angles connected through one leg in tension. This is the expression that is used in the US. So if you have a bolted connection like this, you have a gusset plate, you have an angle, and it's bolted to the gusset plate like so. And this is the center of gravity. And so basically the code says that you calculate how much eccentricity you have. So you have x1 eccentricity in one direction, x2 eccentricity in other direction. You take maximum of the 2, that is your maximum eccentricity. And simply eccentricity divided by L, and 1 minus eccentricity divided by L, that is giving you a factor. You multiply that U factor with the entire cross-section area, entire net cross-section area, and that is your new area. Use that one for your limit state of rupture. It's a much simpler method, right? It is almost similar to what we had before, this alpha value. Now the new method is a bit too complex. Okay, European code also has a somewhat similar approach. If you have a single bolt, there is one expression which is relatively straightforward, still has some dimensions that you have to account for. 2 bolts, another expression. 3 bolts, another expression. So, but these are much simpler, like, just like our alpha values, 0.5 to 0.7, 0.4 to 0.7. So you can take something in between. Fine.
Excuse me, sir.
Yeah. Harish, tell me.
Sir, in the formula you have shown in AISC, sir, American
Yeah.
Family. What is AN, sir? It is only the connected net area, sir.
No. So AN is the total net area.
Okay.
And A is the reduced net area for the eccentricity, to account for the eccentricity.
Total cross section.
Yeah, to account for the shear lag rather. I should not call it eccentricity alone. It's a shear lag.
Okay, sir. Thank you, sir.
Thanks. Okay. Fine. So this was the discussion on shear lag effect. I will also hopefully complete the discussion on how much time I have. 30 minutes almost, right? 40 minutes. So then comes the question of block shear, right? So block shear is discussed in section 6.4 in IS 800, right? For bolted connections and for welded connections also. And the similar method is used for welded connections also. I will give an example for bolted connections, however. So block shear, I had discussed again in the past briefly. What happens when your methods of designing or whatever method was available for staggered connections or staggered bolts stops becoming usable, right? So there is a point when the staggered becomes so bad that you cannot use that equation at all. Remember that discussion? So if I have a plate, okay. So if this is how the bolts are connected, this is not the right way. I think I had given a slightly different example here.
2 holes in vertical and
Yeah, I can 2 holes in this direction. Yeah, maybe somewhat like this.
yes, sir, this one.
Yeah. So let's say you have a configuration like this. I mean, I'm just giving a hypothetical condition here, but let's say. So, and if you apply tension force, then the rupture path obviously will follow this. Correct? Now, as soon as you get here, you are exactly parallel to the tension load. And then your that expression which had P square by 4G, right? Yes, sigma P square by 4G. So that P square by 4G for this part becomes infinity. So that expression fails here. So it is meant for a certain range of P versus G values, not for this kind of situation. This is one situation where actually you are pulling the member in tension, but there is a surface that is going to be under pure shear. And whenever you have that kind of situation, you have to find a different way of calculating this strength. So that's where the requirement of block shear comes into picture. Block shear. Okay. So in block shear, you always have 2 clearly demarcated surfaces. One surface has pure tension, rupture surface I'm talking about, and the other rupture surface has pure shear. Okay. So here is an example just a qualitative example. I'm not solving it. So you have this plate that you are manually pulling, which is connected with 6 bolts here, and it may fail in plane rupture here directly, right? So that is one possibility. But also it may so happen that sorry, yeah, I'm not talking about this plate. Sorry, my bad. We are not talking about this plate. We are talking about this gusset plate. We're talking about this gusset plate. So this gusset plate, when it is being pulled, it can rupture directly from at this location all the way through. That is a possibility. But also there is a good possibility that it will rupture in this shape, like so, and follow ABCD path. It could have ruptured this way also. The entire force was acting here, but depends on which one is offering more resistance, and maybe it may just turn out to be the case that this path was offering more resistance. This path was offering more resistance than this path. So then it may rupture in this way. And if that were to happen, then what will happen is that this surface was in shear, this surface was in shear, and this surface would have been in tension. So you have a combined tension and shear rupture. So for that, there are 2 things that you need to check. You need to check that the shear surface, that is in this case, this surface and this surface. So shear surface is in yielding and tension surface is in rupture. Okay, so first you calculate what would be the capacity if the tension surface ruptures and the shear surfaces yield. Or alternatively, the shear surface ruptures and the tension surface yields. So the shear surface ruptures and the tension surface yields. So either of the 2 possibilities are to be considered. Now that again should raise some questions. What is the next question that should come to your mind immediately? So in one case, we are considering rupture of shear surfaces, yielding of tension surfaces. In the other case, we are considering yielding of shear surfaces and rupture of tension surfaces. And only these 2 possibilities are being considered. And whichever one gives you lower capacity, that is the capacity of this block shear failure. Now, what should be the immediate question that should come to your mind?
Why not rupture in both shear and tension? Why not
Very good.
both shear and tension?
Yes, that is the first question I've written here. Why do we not consider rupture both in shear and tension? That's a valid question, right? If the block shear is happening, it is happening only when the whole thing is coming off. That means both of them are rupturing, the tension one as well as the shear one. But why are we saying that the capacity will be considered only up to one of them ruptures, but the other one has only yielded? So does anybody have an answer?
So maybe anyone from tension or shear, it ruptures first. It will not be able to take as much tension as it have to. So we should consider it as failed, I think.
Yes. Yeah, that is the correct answer. Maybe you could elaborate more, but I think you are, you know the correct answer, but just some more words may have to be added. See, actually what happens is that the rupture is this kind of a situation. After rupture is met, then you don't have any capacity left in that particular mode, right? So let's say you had tension rupture. So the tension surface, this is this surface. If it were to rupture, after it ruptured, what will be the resistance offered by this surface?
None.
Zero.
Zero.
Right? Whereas if this surface were to yield, after yielding, how much resistance will it offer?
Strain on.
How much?
Extra reserve strength of that strain handling would be.
To ultimate, sir.
Yeah, so like at least Fy, ultimate depends on whether you are able to achieve the strain hardening or not. But you are sure that at least Fy multiplied by this area, this much of resistance it will still offer after yielding also, right? Because it has not broken, it has not split into two parts. It is still able to resist Fy load equal to Fy or stress equal to Fy. Fine. Same thing here, whether it is rupturing in shear or yielding in shear. So if it is rupturing in shear, after rupture it cannot offer any resistance, and after yielding it can offer some resistance. So the question comes, so these are the two, I mean, even though there are three surfaces, I am not going to refer to this surface again and again, because whatever is happening here is also happening here. So I'm not going to talk about this at all. I'll only talk about this and this. So let's say both of them, the stresses in both of them are increasing. AB also is increasing, that is in shear, and the stress in BC is also increasing, that is in tension. Now, one of them has higher stiffness than the other, and we don't know which one. If you do finite element analysis or something very complicated, some kind of complex analysis, you would know which one is going to go first. But as a design engineer, it will be too much of work, right? So we will assume that, okay, one of them has higher stiffness than the other. That means that one will be attracting more stress, and the other one will not be attracting as much stress, and that one will yield first. So either AB will yield first or BC will yield first, and the other one would not have yielded. Fine. So let's say AB has yielded first. So the surface that is in shear has yielded first. BC has not yielded yet. Now you keep pulling further, right? Now what will happen is AB will go into strain hardening. After yielding, how much deformation, how many more times the deformation can it take before it ruptures? So at yielding, there is certain 100 times, right? So at the time of yielding, you had only one deformation, let's say. Both of them were carrying the same one deformation. This one did not yield for some reason, but this one yielded. Now, it can deform another 100 times before it goes into rupture. The idea is that the stiffnesses of these two things cannot be so different that this one deforms by 100 times after yielding, and this one does not even yield, right? They are part of the same connection. So this one cannot deform 100 times more, and this one does not even reach a deformation of 1. That cannot be possible. Okay. So the idea is that when this one ruptures, we are guaranteed that this one would have at least reached the yielding point. Okay. Now we cannot say that when this one ruptures, this one also has reached the exact ultimate point, right? Because they may have different stiffnesses, and this may be slightly behind this, or the vice or other way around. But in our example, we are assuming that this one yields first, and also this one ruptures first. When this one ruptures first, this one, we can be 100% sure, because the amount of deformation it would have absorbed between yielding and rupture, that this one also would have yielded, but may not have ruptured. So that's why we'll say one surface, let it rupture, and the other surface, at least you can consider it to have yielded. Fine. Now, because we don't know which one is going to yield first between the two, so we will first do this one, and then we will reverse the order, and we will say, let's consider that this one yielded first and this one ruptured first. Then when this one ruptured, this one would have at least yielded, if not ruptured. So that means you would have another capacity, and then you use the minimum of the two. And that is what you are using. I'm sure you have used this in the past. So in the first case, you are saying shear surface. So this is shear surface, right? So A shear, and that's why you are using Fy by √3 and not Fy. You are using Fy by √3, and shear surface cross-section yielding, right? And net section tension, net section rupture. That is, this one ruptures and this one yields. That is one strength estimation, assuming that this one is stiffer and this one failed first. The other possibility is that the shear surface ruptures because this was stiffer, and the tension surface is lagging behind, and it is only reaching the yield point at that time. So it will have this much of capacity. Tension surface, gross cross-section area, yield stress divided by gamma m0. Okay. So based on this principle, we calculate the block shear failure. Yeah. Now there is this one quick example. This we will solve, and then we can conclude the discussion on this chapter. There's some minor discussion after that about the member slenderness that we will do. Okay, so this is the connection that you can see here. Any questions, by the way, on the block shear failure? Quickly. So this idea was clear to you, right? Why do we consider one rupture, the other one yielding?
Yes, sir.
Yes, sir.
Yes, sir.
Good. Okay. So this is an example. This is a gusset plate. What you see here, this triangular shape. Come on. Yeah. So this, what is this shape name? It's not triangle. What should it be called? Quadrilateral, you can call it. I don't know. So, trapezoid. Yes, trapezoid. Yeah, two edges are parallel. Yeah, I had forgotten that word. So okay, so you have a trapezoid. This is a gusset plate, and that is a typical shape of a gusset plate. Then you have an angle, this one, which is connected to the gusset plate, and this is connected through 3 bolts. And I'm sure you must have done several such examples in your BTech, especially, I mean, when you write gate and all these kind of practice examples must have been solved several times. So the 3 bolts are spaced at 3 inches from each other. 2 spaces are there, 1 and 2. They are 2 at the spacing of 3 inches center to center, and the edge is 1.5 inches away. This edge is also 1.5 inches away from the center. The bolt diameter is given as 7/8 of an inch. The gusset plate thickness is given 3/8 of an inch, but I don't think that has any role to play because we are talking about not the block shear failure or the shear failure of the gusset plate. We are only talking about the failure of the angle. So the plate thickness does not play a role here. The angle is L4 by 4 by 1/4. Okay, so that is 4 inches. Each leg is 4 inches long, okay, or wide, and thickness is 1/4 of an inch. The steel that is used is 36 grade steel. A36 basically has, you can say it Fe415 also, it's the same thing. So it has 36 KSI yield stress and 60 KSI ultimate stress. Okay, and the bolt holes are 1 inch diameter. So if you have bolt that is 7/8 of an inch, so the bolt hole has to be 1 inch. Okay, 1/8 of an inch larger than that. Basically, you have 2 millimeter clearance requirement, right? 1.5 to 2 millimeters clearance requirement. That almost approximately it translates to 1/8 of an inch. So the holes are 1 inch. Fine. Everybody understood the question? Now we need to calculate what is the resistance what is the maximum T it can safely resist. So what is the design T value? Fine. So first we will calculate cross section area, cross section failure. So there are, which limit state will we consider? We will consider limit state of yielding of the angle, limit state of net section rupture, including the shear lag effect. The third one will be the block shear. So gross section yielding, that is this expression, Fy Ag by gamma m0. Ag is calculated as 1.94 square inch. Fy was 36 KSI. 36 multiplied by 1.94 divided by gamma m0, that is 1.1. We get 63.5 kips. Limit state of rupture. Now here, I have done the simpler calculation for an alpha value of 0.7. Okay, why 0.7? What was the alpha value for 3 bolts?
0.7. 1.7.
So alpha was given as 0.6 for 1 or 2 bolts, 0.7 for 3 bolts, and 0.8 for 4 or more bolts. So I've done that calculation here. That is approximate way of calculating it. 0.7 multiplied by Fu multiplied by An. So An will be the Ag minus 1 time the thickness. 1 inch is the diameter times the thickness of this leg. So 0.25, 1.94 minus 0.25, that is the net cross-section area, divided by gamma m1, and I get 56.78 kips. Okay. So this is lower than the cross-section yielding. So between these two, this one will govern. Now comes the question of block shear. So block shear can happen only where the connection is. Okay. So for the block shear failure, the code very clearly. I'll talk about the more detailed calculation here. For instead of 56, in the next slide, I'm doing a detailed calculation also. So that we will discuss in a minute. That number changes slightly, but that does not govern. For the block shear, this is the shear surface. In this shear surface, you have got one surface which is AB and the other one is BC. Which one is in tension, AB or BC? BC.
BC.
So
BC, sir.
edge BC is in tension and edge AB is in shear. So first we will consider the possibility of the shear surface going into yielding and the tension surface going into rupture. The second possibility is the shear surface going into rupture and the tension surface going into yielding. And we use that expression. Now I'm sure you all know how to calculate. If you need help with that, you can use these numbers and figure out. So this is basically 3 times 2 is 6 plus 1.5, that is 7.5 multiplied by the thickness 0.25. So that is cross section yielding. So I'm taking the entire length. When it comes to net section rupture, then I have to remove this length. So I have to take 1 minus 0.25. So to account for this reduction in the length and so on. Likewise, you do this number and you get 43.5 kips in the block shear failure. Okay. So between the three of them, 63, 56, 43, we get 43 kips as the limit, as the design strength of this angle. Okay. All right. Now the question still stays. This was an approximate calculation. What would have happened if we had done the more accurate calculation? So here is that. So again, this is your gusset plate, this is your angle, and this angle is connected with the gusset plate like here. And in this expression, TDN, it is given by 0.9 times ANC FU by gamma M1. So that is your, here it is. So 0.9 times ANC, ANC would be the area of the net area of the connected leg. I have not calculated that separately, but you can calculate. This is the connected leg. What is the net area of this connected leg? Multiplied by FU, that is 60 KSI, divided by gamma M1, that is 1.25. Plus the second part, that is beta multiplied by AGO multiplied by FY divided by gamma M0. So first we should calculate beta, and this is the expression for beta. Beta is equal to 1.4 minus 0.076 W by T, FU by FU, BS by LC. So what we need to know is W by T. So W, of course, is this length, that is 4 inches, divided by T is 0.25. FU by FY by FU is known. FY is 36, FU is 60 in KSIs. BS, your BS is equal to W plus WL minus T. That is calculated. That is 4 plus whatever this was, 2.5 minus 0.25. So that is 6.25. Divided by LC. LC is the length of the connection. That in this particular case is 6 inches. That is LC. And you get 0.64 as beta value. Now, in addition to that, there are conditions that beta should not be more than this expression, which turns out to be 1.32, and should not be less than 0.7. So here my beta has turned out to be 0.64, but it cannot be less than 0.7. So I'm taking 0.7. So 0.9 times this we had calculated just now, explained. Beta I got 0.7. AGO is the area of the gross area of the outstanding leg multiplied by FY divided by gamma M0, and we get 53.3 kips. So 53.3, if you see in the previous slide, 53.3 is only slightly different from about 9% different, you can say. No, in fact, actually 6% different or so from 56.7. Right? So it's not very significantly different. This itself was doing a pretty decent job. Actually, beta turned out to be 0.7, but that was for one of the legs. Anyway, fine. So this is how you can calculate the tension strength of any angle. Other members is much more straightforward. Any questions so far? Otherwise, we are at the very last slide. Okay. So now, in addition to this design provision, we also have to be mindful of the slenderness values for the member that are allowed for tension members. So even if the member is in tension, if there is any likelihood of the member going into compression, so if the member can undergo compression because of loads which are not earthquake or wind. So earthquake wind loads are temporary loads for a very short duration they come, right? So except for those loads, if the member can undergo compression still, so it could be from the live loads, it could be from vibrations, it could be from, that is also a live load, or gravity loads, or for whatever reason, then you need to consider that member as a compression member, and KL by R of that member has to satisfy this limit, and that R is R minimum. Okay? So it has to satisfy this limit. It is just like it's a column in a way, or it's a main leg in compression member. Okay? So it has to be the most stringent requirement. However, if the compression in that member is coming only because of wind or earthquake, then you can go up to 250. So you are the KL by R limits are relaxed. Where could this be? Where could you have this kind of a situation? So if you have a roof truss, for example, if I have a poorly drawn roof truss, okay. Under gravity loads, the bottom chord will always be what? Where is the bottom chord? This one, right? So under gravity loads, the bottom chord will always be in tension. But when the wind loads act, sometimes the wind loads may have a kind of this kind of a pressure from inside out. Okay, and that can cause this. If there is a, let's say, imagine that there is a sheathing here, there is a roof here, and that roof is being pushed up, then you may have the bottom chord undergoing compression. So this bottom chord, you can have KL by R up to 50. 250, sorry. Yeah, you can use this limit for such kind of a member. But any other member which can be under compression for any other reason other than wind and earthquake, you have to keep that limited to 180. Okay. Then if there are members which are always under tension, no matter what, even wind, earthquake, whatever it comes, if they are always in tension, then you can have KL by R up to 400. Okay. So like there may be members which are like there may sometimes be some such members, but still there are other types of members which are used as pre-tension members. Like, you know, in PEB, pre-engineered buildings, you have, how many of you know what is a pre-engineered building? Pre-engineered steel buildings.
Generally uses pipes and
No, it's
rehabilitation purposes.
Louder, sorry, I couldn't hear you clearly.
Generally used at construction sites and the rehabilitation purposes when disaster strikes or so.
No, so not so much for rehabilitation. I mean, these are serious structures. Typically, they are industrial structures, not so much for rehabilitation.
they will have a tapered section, sir.
Yeah, so the columns are tapered, the beams are also tapered. Yeah, so these are basically moment resisting frames.
Yes.
The way they look, maybe I can quickly draw. I didn't want to spend too much time. So there was a time when industrial structures were made with roof trusses, the kind I had shown just now. But nowadays, PEB is much more popular. You must be laughing at me that how hard can it be to draw a straight line? See, it gives you some appreciation for kids, you know. So kids have to learn to draw on pen and pencil, like, you know, on pencil and paper, and how hard it must be for them to learn to draw on new devices that they have not used in the past. So this is how these typical cross sections look like. They are not, of course, it should be symmetric. Yeah. So you have heaviest section right here. So it is typically, it goes like this. So these are the stiffeners. Sometimes you may have a diagonal stiffener also. Okay. And then you may have some other stiffeners along the way. I'm not drawing in full detail. So basically, the way these are made are, these are not hot rolled sections. These are I-beams but these are tapered I-beams. So basically these are plate girders. So they take one plate. So these are basically plate girders which are welded together. So they do the welding. And all they do is that the flange thickness and width remains constant. So as you move from here to here, the flange thickness and width, it's the same plate, doesn't change. Similarly, this flange. What changes is only the depth of the web. So web thickness also remains the same. Only the depth of the web is changing. And then you put one flange above it and one flange below it. Okay. So that's how these cross sections, these are tapered sections. So that's how mostly nowadays the industrial buildings are made. In older times, industrial buildings used to have this kind of a roof, and then there was separate heavy duty columns. There was some kind of a roller connection here, and these columns were anchored and all that, right? And columns had to carry that load. Now that lateral loads are not carried only by the cantilever columns, but through this frame action. Okay, so if there is a horizontal load acting, it leads to a compressive force here and a tensile force here. That was not available in earlier structures. Earlier structures, if there is a lateral load acting here, it had to be resisted only through a moment here. Okay. Anyway, so this PEB type of structure, they often have something called tension braces or sag rods or something like that. So basically, this particular diagram that you see here, this figure, this is for one frame. So similarly, like I'm looking in the plane of this frame. So this frame will look somewhat like this, and likewise there will be another frame. Okay, and often what you may have is some kind of a brace connecting these two frames together, cross braces, and those cross braces will be pre-tensioned. So at the ends, these cross braces will have some kind of a thread. And so if I can zoom into this area, so this rod will be coming in, and it wants to be, let's say you have a plate that is a part of this frame. My drawing is getting worse and worse. So basically what you do is you have some kind of a thread in this brace, and then you put some kind of an anchor and or some kind of a bearing, and then you put a nut here, and then the nut is tightened so that this rod undergoes tension. So then you can maintain tension throughout the loading, right? So because the rod does not have any compressive strength, but it is, you pre-tension it so that it is in tension when the earthquake loading comes. So it either goes into, even if it goes into compression, what will happen is that this contact will be lost and there won't be any compressive force coming onto the rod because it is only in being pulled this way, right? So it can resist only tension. When the compression comes, it will simply separate and will not resist any compression. So that's how these systems work. So if there is a wind load acting in this direction, so if the wind load is acting in the plane of the frame will resist. But if the wind load is acting perpendicular to the frame, then these braces will resist that. Okay, that is how this designing works. So if the wind load is coming this way, this brace would go into tension. Of course, there is there are horizontal members also which are connecting the two. So both of these will move, and this brace will undergo tension, this particular brace. And this brace does not have to undergo compression, as it is going to either lose contact or it is already in so much of tension that the tension will reduce only. It will not really go into compression. So for such members, you don't even have to satisfy any requirement of L by R. So you will see that these are very thin, long rods, and they offer enough resistance. So if they are pre-tensioned, then you don't have to have any limit. But as long as they are hot rolled sections which are not pre-tensioned, then you have to have a limit of minimum 400. Now, this is even in, so 400 limit is for the members for which you are guaranteed to never have any compression coming in. There is no fear of any buckling at all. Still, you have a requirement of a minimum slenderness. Can anybody suggest why? That is the last question for today. So
that may be because of the self weight, sir. For this, because of the self weight, there might be some kind of bowing out, and which will make the load be eccentric.
It's anyway going to be only in tension. So even if there is some, see, first of all, self weight would be very small in comparison to the member loads that would be acting. And I mean, even if it is bowing, bowing does not affect, or imperfections do not affect the tension behavior very much. Bowing has a very critical role to play in compression member. But for this member, we are saying that compression it's guaranteed that there won't be any compression. So that is not really a major reason. How it behaves in the structure is not really a major reason, because it is guaranteed in a way. As long as, I mean, you can guarantee that it is never going to go in compression. Any out of stateness or any bowing or anything will not change the tension behavior very much. Anybody else?
So maybe when slenderness ratio is very long, the length is large, then sag would be very much that will not.
That is almost the same thing what Prithvi was saying. That is the correct answer. I mean, I don't have a problem with that. I mean, there may be some deformations, but overall, it will not change the behavior of the structure. So let there be sag. As long as tension is concerned, it will still, when the tension comes, it will resist that tension in spite of the sag. The problem is not during the when it is part of the structure already. The problem is when you have to transport it, when you have to erect it at that time, because then the self-weight, the same self-weight that you're talking about, but that self-weight is not acting when it is a part of the structure already, because then it's okay. But when it is not a part of the structure, at that time, there are still other types of loads acting on it. That is self-weight, there could be vibrations, there could be, you may want to hold it in various configurations, vertically, horizontally, when you are trying to erect it. And at that time, it should behave like, so if you want it to remain straight, it should remain straight. So it is during construction, during transportation, during fabrication. At that time, it should not deform too much. Otherwise, it will create issues for connections, etc. Or like, transportation, etc. So if it is very flimsy and it is vibrating, so you put it in a truck and a part of it is extending and it is vibrating so much because it is so flexible. Okay. Something like that. Or you lift it with a crane and there is a little bit of wind and the whole thing starts vibrating. Something like that. So from those considerations, you still want to maintain at least a limit of 400 for these members. But there are still other types of members, which are rods, for example, which are pre-tensioned. For them, you don't even have to maintain that limit. Okay. All right. So that is the end of today's lecture. Any questions? In the next class, we will start talking about compression members. Any questions? Please shoot.
Sir, can we say that slenderness ratio is a stability parameter, sir?
Yes, slenderness primarily governs the stability behavior of the structure or the member. Yes, that is true. Because slenderness, where do you get L by R? This R, the concept of R or the concept of L by R, this comes from your pi square EI by L square, right? So because the relationship between L divided by I or L square divided by I, that is primarily coming from your Euler-Buckling equation. Okay. Any other questions? Okay, fine. So thank you. Let's call it a day.
Thank you, sir.
Okay. Yeah. Bye. See you next week.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you. Thank you.
Thank you, sir.